I think my real interest, if I traced it back, was curiosity about the physical world, which is what physics is.
One might imagine, at least, that one's talking about nature when one's talking about the character of physical laws. But I don't want to talk about nature, but rather how we stand relative to nature now. I want to tell you what we think we know, and what there is to guess, and how one goes about guessing.
This is the piece of the equation which describes how the Higgs field acquires its value.
So welcome to this episode number 64 of Physics Matter Colloquia series, and good morning or good afternoon to everyone. So my name is QuSyn from the European Spallation Source in Sweden, and we are joined today by Alan Hurd from Los Alamos National Lab. So we are both former chair of the Forum of International Physics, the FIP, at the American Physical Society, where here, so Charlie Ballet is representing. And we are proudly supporting this colloquium series. So since 2020, Physics Matter has highlighted how physics and international collaboration can contribute to scientific development and global challenges. So all our previous episodes are available through this FIP channel and the webpage for anyone interested in strengthening scientific community worldwide. So last year, during the International Day of Quantum, we organized a series of exciting discussions, so 12 of them, on the Physics Matter channel. As well, in collaboration with UNESCO and the International Union of Pure and Applied Physics, the IUPAP. So in particular, in October, the IUPAP and UNESCO webinar explored the growing intersection between the quantum science in industry, with contribution from leaders across academia, research laboratories, technology companies, including Microsoft, IBM, Quantinuum, and emerging quantum startups from several regions in the world, where also Urbasi was presenting. So we had features of Professor Yassera Ismail, who shared her vision on building Africa's quantum future, strengthening the research and innovation capacity last October on the Physics Matter channel. But today, we are delighted to continue this global perspective with an Indian quantum ecosystem through the vision of Professor Urbasi Sinha. So Professor Urbasi Sinha is a leading experimental quantum physicist at the Raman Research Institute in India, a Canadian excellence research shareholder, a founder of QuSyn Technologies. Her pioneer works in quantum optics, interference, and quantum communication is positioning her at the forefront of Indian rapidly growing quantum research and innovation ecosystem. So Professor Sinha also plays a central role in India National Quantum Mission and is leading a consortium of institutions developing entanglement distributed-based quantum networks. So it's a great pleasure to welcome Professor Urbasi Sinha today. So we will have about 40 minutes of her presentation. You can ask your question or write them. So we will answer by the end of her presentation. And now, so Professor Sinha, so the floor is yours.
Thank you so much, Christine, for this warm welcome. And of course, it is a great pleasure to, be back in a forum which involves you as well. Your enthusiasm is, of course, very motivating, as it was the last time. And thanks for this very kind introduction as well. So I will go on to sharing my screen, which we successfully did a few minutes ago. And I would like to also go to slideshow mode. Yes. So everything still works well for all of you?
Yes, very well.
Yes, great. So thank you very much. Yeah, it's a pleasure to be speaking in this very prestigious forum. In fact, the original plan was to speak in February, but something else happened. So now I'm very glad that we are finally doing this and, at a very good time as well. So my topic is on quantum foundations to field deployments, and it is going to be an Indian journey. So I'm going to talk to you about how, as a country, we have proceeded from foundational research to field deployments. And of course, I will use our own research as a lens wherever possible, because that gives it more, it is less abstract that way. Otherwise, it just becomes a bunch of words. So as was mentioned, I'm a senior professor at the Raman Research Institute in Bangalore. I also hold a Canada Excellence Research Chair professorship at the University of Calgary, and I'm a co-founder of QuSyn Technologies, which is a deep tech startup. So essentially, this is going to be the thesis that I'm going to follow for the talk. As you can see, it is going to follow this particular arc from proof to trust to capability. So first of all, what we need to understand in quantum, whether it is communications or any other domain, is whether the physics that we are actually basing everything on actually works or not, right? So that is the first thing we do. Then we go on to using this, the output from the physics and seeing whether this is actually certified or not. Can this actually lead to infrastructure going forward? And finally, when we are satisfied with these two steps, it becomes a capability. And so the question we ask is, can it become national capability? So this is the sequence that my talk is following. And it is also a practical route from science to systems. So our national policy, as well as our labs, evolution, both seem to follow exactly this particular arc. Okay. So, well, quantum is becoming infrastructure. I think we are aware of this, and I'm quite sure that many of the people in the audience are also from this domain or are excited by this domain enough to know that these are the sectors which really matter for India's, aspiration of becoming a developed nation in 2047. Vikasit Bharat is actually the Hindi for developed nation. And so in order to become a developed nation, we are actually prioritizing emerging technologies very, very strongly, and quantum being one of them. And we do believe, not just in India, but globally, quantum is going to have tremendous impact in various sectors which matter to society at large, right? Whether it's communication, health, energy, transportation, finance, space, agriculture, defense. So essentially everything around us will have a quantum feel to it, right? However, one thing I, of course, would always say in every talk that I have given so far, and perhaps will continue to, is that this is one area where, the focus is pretty much there. But with that comes a little bit also of what I would say is hype. Right? And so we are in a bit of a hype cycle for quantum. Various brochures have discovered quantum. In fact, this is a very interesting material that was found available a few weeks ago. And so you can imagine that, the word quantum is appearing in different kinds of brochures, which is all right. But then people like us who have been in this business for more than 25 years, we learn to live through this and hopefully outlive this. And that is how the contributions become national capability. This is good because the focus remains resources are necessary, but we need to ensure that we don't get carried away by the non-scientific aspects of the problem. So this brings us to, of course, India's National Quantum Mission, which is a very, very exciting initiative, as we know. And this is an example that, India has chosen to play the long game. Okay, so we know that India is currently a developing nation, although, I would say it's in between developing and developed, whatever the, markers for that are. And so India is the first country in the world to have a national quantum strategy as a fully developed nation. And that is actually brilliant because, we do not want to follow. We want to be in a situation where we understand the urgency before it becomes a necessity. And we want to develop the architecture. We want to develop various technologies so that we go towards a sovereign country and we become self-sufficient in the quantum domain as well. And so the 6,003 crores, it roughly translates to some 700 million US dollars. And then along with other investments that have happened, it's a $1 billion investment over the course of 8 years for various aspects of quantum technologies, whether it is, computing, communication, sensing, metrology, materials and devices. So this is what is important about the National Quantum Mission is not the verticals we have chosen to work on, because these are pretty common across the world. These are the areas people are working on, but it is the timing of actually this investment, because the investment is before urgency becomes dependency, and we do not clearly want to have that happen. And so this is why NQM is very special, and it is not just about funding individual projects. So of course fundamental research has been extremely strong in India for a long time, right? But then now we are translating from fundamental research towards technology, and that is towards building an ecosystem. And so this is the map of India, and as you can see, we have like 4 thematic hubs which have already been formed. We have 14 consortia under them which are looking at different aspects of quantum technologies. Similarly, 43 institutions, 152 researchers. And this is a bit outdated because with the quantum algorithms kicking in, these numbers have almost doubled. And so as a country, we have really spread out the resources to many different avenues and many different researchers, so that we actually come together as an ecosystem. It's not a project funding. It is funding which brings an entire group of people together. Okay, and this is very nice because it's not in silos. We work together, and that is what leads to things which go beyond what we can perhaps achieve as individual researchers. So it's beyond individual brilliance and bringing together brilliant people to have something even more brilliant. So that is the idea. And so, as I said, in order to explain this arc that we are following from proof to trust to capability, I will use our own research in the Quantum Information and Computing Lab at RRI to sort of provide a lens to see how this actually works, because many people, again, may not be from quantum. So what do we mean by these various steps is very crucial for us to understand. And so this is why, it's not a CV, it's essentially a case study of the same arc. Okay, and so 2012 is when our lab's journey began. And we have done a lot of foundational experiments, fundamental physics experiments, and we continue doing them. And some of them now actually are translating to technology and to even product level. And this is the journey I will sketch over the next period of time that we have in this colloquium. And so we have the fundamental experiments, we have proof, we have certification, and now we are looking at repeater networks, which is of course most modern in terms of technologies as it gets. As I like to say, the photons were patient, but the humans learned to be. Of course, as young people, of course, I won't call myself young, but we're surrounded. Academia is great because, on an average, our age does not change, because I have a first year undergrad who's working with me. I have PhD students, I have postdocs, and of course, I am increasing in age, but the overall average remains same. So you remain enthusiastic and curious. And that is, of course, what forms the basis for a lot of the success that we have, our own curiosity. So photons, as you know, are single particles of light, and for our work here that we do, they carry the story forward. Photons are the ones which are used as test beds for fundamental principles of quantum mechanics. Whether it is all the seminal experiments in quantum, whether it's Bell tests, whether it is tests of superposition, many tests have been done using photons. Again, photons are the ones which lend themselves towards making the fantastic, devices, integrated photonic devices. And then, of course, field deployment cannot happen without photons, because photons are the carriers of the information. And they are brilliant in doing that because they can go a long distance without interacting with other matter particles necessarily, because they don't have charge and mass. And so in some sense, they are the perfect carriers of information. And that is why they are the chosen, mostly the chosen particles for communication experiments, right? So having said that, slowly moving towards a particular theme of quantum technologies, because as I was telling Christine before we began this, I could have just done a lifetime achievement talk where, I hope I get to live a little longer than this, but then, and we could cover all verticals of quantum and what we have done in the last more than 14 years in the lab, but that would not really be very interesting from this thesis that I want to share today of an arc which is what the country also is following now. And so for that, I have chosen quantum communications as the focus area, and one of the developments, and maybe a couple that I will discuss. So when we talk about quantum communications, of course, I think we know that, when we, for people who are not from the field, let's say, you use light to communicate anyway, right? And we have these fibers, I'm speaking to you through internet, obviously. And so light, electromagnetic waves, they are a common choice. But then, there are things about light, for instance, which come in handy when you want to have this communication over a long distance. So whether it's, you can copy them, you can copy the states, you can repeat the states, you can have routers. We know we have wireless routers and so on. So these are all things which are allowed in classical communications. But now the same light, when you now use it as a photon, let's say when it's the quantum particle of light, these properties are not allowed. Okay, so you can't copy an unknown quantum state there because of no cloning theorem. You can't just simply repeat something, again, the same problem, and you can't just scale up. And if you want to really peek and see what is going on, that's also a problem, because then that gives rise to the disturbance, which again is detected. So quantum communications is hard because, things which we take for granted in classical cannot be done similarly in quantum. So we have to think out of the box. We have to now make use of laws of quantum mechanics in an innovative way and come up with paradigms which can allow a very different layer of security, right? And so this is why this is not a device. A quantum communications area does not talk about one device or the other. There are different layers and it's a stack. Okay, so the transport layer gets a lot of attention. If you look up things in quantum communications, you'll see, records being broken about fiber QKD, or whether it's free space. Our neighboring country has shown satellite QKD some time ago. And so these are things which get a lot of focus. But then you have to remember that this is not the only thing, because then comes the second layer, which is of trust. What I'm doing right now, is that actually certified? Okay, the random numbers I'm using as the basis for my security, how good are they? How is my device integrity? Because without this transport layer is not going to be very interesting. Okay, then comes the even harder problem of interoperability. Now I have these distances, I am doing something, I'm communicating something, but are these links actually talking to each other? We have to give them some time so that they can meet. So we need quantum memories. We need transducers. We need heterogeneous nodes. And so this is a very hard physics problem still. It's one of the most physics-oriented, areas in quantum technologies, because there are no obvious solutions yet. There are some contenders, but none of them is a clear winner. Capacity, can I extend that? So this is the focus today, to also explain that it is about trust, interoperability, and capacity upgrades using photonic quantum science. Because, distance without trust is expensive optimism. Yes, just having a distance declaration without an underlying trust layer and all these layers is not going to take us very far. So this is what is quantum communications. And as I said, what I want to do over the course of the talk is take you through an arc which goes from, proof to trust to capability, and also define what I mean by that as I go along. Proof is, of course, exactly what it says. Does our quantum system do exactly what we claim it does? And this is a very important question, maybe not something we are asking all the time, but then we need to, because, suppose we don't have any proper checks and balances on whether the quantum system is behaving the way it is supposed to, then whatever we build on top of that is, of course, pointless. Yes, proof is a very important layer. So which brings me to a very interesting concept, which is not perhaps discussed a lot, but then it is currently I think 7:45 p.m. IST, so it's kind of a long day, so a little bit of wondering is allowed so far as I'm concerned. And of course the wondering that I would always do is that there is quantum here, quantum there, quantum everywhere. But what does quantum actually mean for you and me? So I've been also speaking a lot about quantum over the last few minutes, but then me, Christine, or anyone else in the audience, if I were to just run and, hit my head against the wall, which is right here, am I going to tunnel through? Or am I going to get really injured? The probability of the second one is almost 100%, right? So, but then tunneling happens, right? So these weird features, quote unquote, that we talk about, whether it's superposition, whether it's entanglement, so many other things, what do they mean in our everyday life? Yes. It makes sense for the micro world, yes, but what about the macro world, your world, my world? Do these phenomena show up? Of course they don't. We don't really have tests of entanglement between humans, for instance. So this is the question that, of course, bothered many great people, and the question is, can we test quantum in the macro limit? Yes. So micro is fine, but how far can we stretch this? Where will this start failing? Okay. And so does nature differentiate between micro and macro is the question. So the answer to this, of course, for the people who already are familiar with these terminologies, you know that we talk about these local realist inequalities. We have these two-party or multi-party systems which share this correlation called quantum entanglement. And then we can do experiments to measure what are called Bell inequalities. Okay, and so if you violate Bell inequality, then you are violating local realism, and that serves as a proof that the underlying theory is also, validated. Okay, so this is all fine for entangled systems, more than one particle in the usual sense. And then comes along Sir Anthony Leggett, who actually asks the question that, this is okay when we talk about precisely two or more parties, but then what about a single system? A single system is also as quantum, as two systems which share entanglement. And how do we test for realism, which is a finite test, to see what happens? It's a finite proof test, I would say. And so he asked this question, and he, along with his then postdoc Anupam Garg, they came up with the time equivalent of Bell inequalities in some sense. So here now we can have inequalities which now cater only to a single system, not systems which share entanglement or more than one system. Okay, and so what is the notion of realism? Why is it important in the context of quantum mechanics? Because violation of realism actually tells you that quantum is fundamentally different from classical. So now, just to give you a little example of what we mean by this concept, without getting into the details, because it's a very technical topic. But then, realism essentially means that if I'm here, I'm talking to you, I'm wearing a pink shirt, okay? But then if you sort of go to the washroom and come back, you would expect that I would still be talking to you and wearing the same shirt. So my property, let's say, of wearing this shirt is not dependent on what you are doing. So in some sense, a system has properties independent of measurement. Okay, that is realism. The moon is there when I'm not looking at it is a very famous quote attributed to Albert Einstein. But then in quantum systems, that is not true. A quantum system can have one in many, it can exist in a superposition of many different possibilities. Only when you measure, you reveal a certain property. So it's fundamentally different from what I just discussed. Okay, like we have the famous example of the Schrodinger, of the cat, and of course we know the Schrodinger cat. This is the cat, which is sitting in a radioactive chamber, and we don't know whether the cat has been exposed to the radioactivity or not from outside. So in some sense, it is in a superposition of being dead and alive. Okay, and so this is an example of the weirdness. Of course, the cat is not hardly quantum, but this is how the example goes. Okay. So having said that, there are different, as I said, tests for probing this. We have realism and locality, which gives us Bell's inequality. But then comes the Leggett-Garg inequality, which is the time equivalent of the Bell, where we replace locality with another concept. I won't get into the details. That's also a very technical one. But then violating it, again, is going to violate realism, which is going to give us the same understanding of the underlying theory. Again, the proof. Okay, so this is Anthony Leggett and Anupam Garg. Of course, this picture of Anupam Garg is not when he was his postdoc. Clearly, it's in his more recent years. So this is the temporal analog, and essentially certain concepts are introduced here which are different from the Bell. So having said that, original motivation for this set of tests was to use it for the purpose I just talked about, that how far can I stretch quantum, when does micro stop and when does macro come in, and so on. Lots of experiments have happened trying to change the size of a particle, trying to change the mass of a particle, and seeing where things break down and so on. But more recently, it has become interesting to actually use it in a single particle case as well, as a proof for the underlying theory, as a proof layer, as I like to call it. Okay. So this brings us to these, various tests which happened in the Bell scenario, which are these loophole-free Bell tests. Now, having said that, what is a loophole? Okay, so I'm slowly warming up to the main idea that how is this related to quantum communication? So we talked about Leggett-Garg inequalities, time equivalent of Bell, violating them proves something about the underlying theory. But then comes the point that, all these experiments, it's not just the Leggett-Garg or the Bell, any experiment in quantum optics suffers, from different kinds of fallacies, let's say. Okay, no experiment is perfect. So for instance, if I use photons and I'm detecting the photons, and that is how I'm violating these inequalities, but out of 100 photons that are incident on my detector, I know that only maybe I would be able to detect 60 or 70, depending on the quantum efficiency of the detector. So what happens to those 30 or 40 I don't detect? Right? So then I can't comment on their behalf because I have not even measured them. So this is called the detection efficiency loophole. A loophole is a legal term. So, it is used in a court of law and essentially, as I say, that, a loophole is what happens when nature hires a good lawyer. So if you do something, but nature comes up with an alternative explanation for it, then you cannot call it loophole free. So then those things remain as not only issues with the underlying physics, but also they can be used by adversaries to come up with attacks on your system. That's the other part. So closing the loopholes turns a compelling result into a definitive one. So a loophole-free architecture is somewhat the gold standard in our community, because once you have that, then you know that, okay, this is the best that can happen at the given time, then I can use it for security. Because if there's a loophole, then I'm always worried that is it really completely secure? No, because somebody can come and use that loophole and get my information, right? And so this is what makes this such an important achievement. And this is a beautiful article in Physics Today on this problem, which I'll encourage the students in the audience at least to read, because it tells you that, a loophole free is important, not only because the underlying theory is okay, that is great, but it is also because, we know that we have particles that are not only entangled, but a particular source is working as intended and hasn't been tampered with. From an application perspective, this is even more important, let's say, because we can now have, I won't say perfectly because this is Physics Today, so it's a little bit more generalized, but I would say that we can have information theoretically secure quantum key distribution and a new class of random number generators which are going towards what are called device independent randomness. Okay, so, and in fact, that brings us to our own experiment, which we did a few years back, where we did, for the first time in the world, we performed a loophole-free violation of the Leggett-Garg inequalities. So, Leggett-Garg inequalities were discovered in the 1980s, and several experiments have happened after that, where people have closed different loopholes. Okay, but all the loopholes together for the first, was not done before. And similarly, there were loopholes like detection efficiency loophole, which weren't even considered in previous experiments. So our experiment actually closed or circumvented this together for the first time. And this is not just important because it's always nice when you do something for the first time. It's also nice when you do something which people have been trying. But it is nicer because now we have an architecture which can be used for a higher level of security. And that is what, so these are all reasons which motivate us to spend so many years. This experiment took like 5 or 6 years to actually accomplish. And it was, of course, beautiful when it all happened. And so this is the result, by the way. I won't get into the details of it because I know this is, not a very technical expectation in the colloquium, but then I would like to point out this still, So this is what we expect from quantum mechanics for these violations, and this is what we get experimentally. And you can see the match is beautiful. And that is something which we have to talk about. This was something which was a dream, and that is how we went on to do that. And very nicely, we got some very nice feedback on it, especially from new scientists who called us the most watertight experiment of all time, which indeed is very nice going forward. So having said that, this was the loophole-free experiment, which is an example of the proof layer, a very strong example of the proof layer, because it's even loophole-free. So now comes the point, okay, so I have this, now what? Yeah. So we won't just stop there. So we want to see, can we do something about the trust layer? Because after all, trust is also necessary. So before that, we also went on to show that this works very well on even noisy quantum computers. Okay, so it's not just something which is working in my own experimental device, which I have very nice controlled environment in the lab, but it's also working on somebody else's cloud-based system and the hardware, which we know is noisy. Okay, and so this was a very nice use case for quantum computing and quantum communications. So proof becomes useful when it certifies a resource. Okay, and that is when it becomes trust. Of course, it is useful nonetheless, but useful in the sense of societal use, right? So trust layer. So when proof becomes certification. So now, as I already hinted, that the trust layer in this story, whether it is the LGI story, whether it's the Bell story, so many other parallel stories, would be an application in security. Right? Because of course that is where you need maximum trust. We live in a world where we don't always trust each other, let's face it. And so naturally we need to come up with ways to protect whatever it is that we feel is worth protecting, and that is what brings in the need for security, right? And so randomness, random numbers, they are very, very important in many different areas. I don't know where the audience is coming from, but if you are in simulation, weather, materials, models, finance, risk, fraud, sampling, but security. Modern security runs on unpredictable bits. Yes, and so in fact, random numbers form the crux for the security that follows. And so their quality and their trust in them is very important. But what is beautiful is that realization that we built global security on randomness long time ago. But then only later on, over the last few years, we are asking the question whether the randomness was actually random. It's sensible, but a little bit late. But nonetheless, better late than never. What do we mean by actually random? Now, okay, you have random bits. You can run it on some, classical, something like a NIST, a suite of tests or something, and you know that you have random bits. But that's okay. But then comes the question: do I trust the source of randomness? Is there any certification involved in how I'm generating these random numbers? Or, I generate random numbers painfully by using some method, and then somebody among you, let's say Christine again, because I know her the best, comes and actually copies it on a USB stick and also becomes a source of random numbers herself. So how will you as a third party distinguish between us? Because you will run these same tests and both of the random number bits will pass those tests. But then one is clearly certified and the other is not. So you need a step where you certify these random numbers. Something has to happen in parallel that tells you, okay, because this is happening, I know that my source is random. And I don't care if there is tampering. I don't care if there is aging, so long as this keeps happening. The certification step becomes very important. And now if I look at the whole trajectory of random numbers, of course, throw off dice is a source of random numbers, but it could be imbalanced, it could be biased. Pseudo-random number generators, I'm sure all the students in the audience can write a code in 5 minutes to generate them because it's algorithm generated. It also becomes predictable very easily. Then we go on to true random number generators based on laws of nature and so on. And among them, quantum random number generators. And this is an example, of a quantum random number generator, the first of its kind, where you have a photon which is hitting a 50-50 beam splitter. Because it's 50-50, there's a 50% probability of it being transmitted and a 50% probability of it being reflected, which makes it random. Okay, so far so good. But then all of these things, they have a certain problem that they are all dependent on the device. So, suppose your beam splitter is tampered a little, or as we know in the lab, a beam splitter which started off as 48:52 ratio slowly goes towards 40:60 because it ages. So then, of course, your random numbers are not particularly random beyond a point. And so it is compromised. So both aging and tampering can compromise all these classes of random numbers. And that is what brings us to this thing about device independent random numbers, where there is a certification already involved. That, whatever happens to the device, if this certification step is also happening in parallel, I know I can trust my randomness because that is directly linked to the minimum entropy bound. Okay, that is the technical way of looking at it. And so Bell inequality violation gives us that certification. But then comes the point, okay, So what did we go on to do? We actually used our Leggett-Garg inequality violation and the loophole-free architecture to generate certified randomness from such inequality violation, again, for the first time. And we achieved a very successful RNG. And at the moment, of course, we have higher random bits and more speed and so on. But then that was not the point of this. The point was to show that this actually works. And so both the theory and experiment are available in this publication. But then now comes the point that, these are all various, publications from different groups globally, some of a snapshot of some of the seminal ones, but there are others which are also equally important, where you can see that Bell inequality violation has been used to generate random numbers. But then, of course, if you see the trajectory here, the last column, you can see that as soon as we reach the loophole-free Bell, the distance that we need between these stations is around 200 meters. Why is that? Because if you're closer than that, then maybe you can bias each other's measurements by violating because you can violate the locality loophole. Essentially, what that means is that you can just make a phone call and say, do these measurements, and the other guy does them, and you show a violation, but it's not real. Okay, so you can bias each other's results if you're within each other's light cone, and so then you need to be 200 meters or beyond to achieve this kind of randomness generation. But that brings us to an interesting question, which I'm hoping some of you are asking yourselves, that 200 meters, it's not very, you have to walk a little in order to reach your Bob station, right? And so this is great from a proof of concept, but can this really be taken to the next level where it becomes useful for the sectors that it is supposed to be useful for? Can I expect my financial sector or my defense sector to use a device which is 200 meters long? Obviously not, because it's not a device. It's a very big resource. Our generation of randomness comes in now because we are talking about single systems, right? Single systems moving ahead in time. And so space becomes irrelevant here. And so the experiment that we did in the lab took only, a small amount of space on an optical table, 1/3 of an optical table in some sense. And now we are actually making it even smaller. So this is how, trust can actually lead to devices and deployment. Okay. And so this is what I meant by the certification. Just to recap that, you have an input, you have a random number generator, and these are your bits. Well and good. But then certification is the question, and device independent certified randomness generation from Bell inequality violation sets the benchmark. It has been done, for the last decade or so, but our temporal correlations opens a new single system route, which also is amenable towards an actual product. Okay. And so this is what it is, this is the arc, right? So if you see here, this is the loophole-free experiment. This is how, it looks, of course. This is the schematic with actual optical elements, as you can see. Then we went on to generate these true random bits using this architecture. And now, as Christine already mentioned, we also have a startup for the last couple of years, and with the focus product that we are focusing on here is QRange, which is going to be the portable and product version of this random number generator. So this is an example of physics going to certification, going to device, and finally deployment. Okay. Similarly, we have traced this arc for other experiments that have happened in the lab as well, whenever that is possible. But please remember, not every fundamental physics experiment is going to become a device and a product. That is a mistake. To think that way, but some of them can, and so we have been actually painstakingly following this journey for whichever ones are amenable to that. Okay. And so that is the idea behind QuSyn Technologies, which is, following this arc from foundation and validation to practical certification to deployment. Okay, so this is our startup, which was registered in June 2024. And I'm very pleased to say that, we have lots of different kinds of people who are forming the executive team at QuSyn now. So this is, of course, me, and this is Professor Anindo Sinha. We are co-founders along with Dr. Kallol Sen. And we are, of course, all from an academic background. Dr. Devadutta Ghosh also is she's currently the CTO, and she's also from an academic background. And so we need, of course, people who understand quantum, who know what can happen, and more importantly, what cannot happen. But then these are, of course, very important, equally important, if not more important, people in our startup, who are our business development and operations management people, and also shareholders who are not from the quantum background. And I think that is very important, because I think we should stick to our strengths here if we really want this to succeed. And so that is the whole idea behind this. Brain. This is actually, as you can see, of course, Kollol came up with it. It was supposed to be the brain, and these are the different aspects of the brain. Okay, so that is that. And so that brings us to Q range, so from proof to device to certification to deployment. So we have Q range, where you can see, this is, of course, the whole, banking security layer. I won't get into the details of all the layers. That's a bit much. But then this is the layer that we should highlight here. There is a TRNG, a true random number generator block inside, okay? And this is a hardware, and it is a physical noise source. And so what we want to do is replace this with the random number generator from, these sort of violations that we have been studying for the last 10 years. And this is the idea, security depends on randomness in the banking system as an example, but any other, system which requires critical security. So then you have the entropy source, which is the TRNG, but this fails quietly, okay? Hardware aging, faulty architecture, firmware bug, power fluctuation, side attacks, all these make it fail, okay? And keys become then predictable, which is the beginning of the end. Because if this becomes compromised, then your whole security is compromised. So our semi-device independent QRNG is aimed at fixing this root cause, okay? And this is a little bit of a show-off slide, I would say, although it doesn't quite look very flashy. But then, if you think about it, these are all the device-dependent QRNGs, which are currently available solutions in the market. And if you see the various criteria which are necessary for RNGs, trust model, calibration sensitivity, spoofing resistance, tamper detection, noise, audibility, failure detection. So as you can see, most of them are not particularly scoring very highly here, whereas in our case, because of the DI nature, the device independent nature of the problem, we can come up with a solution which is obviously much stronger than the existing ones. Of course, currently we are in the stage where we really need the resources to be able to get this product out in the market, and we are hopeful that that is going to happen very soon. So the idea is, if you trust the physics in this little box, you can trust everything built on top of it. And if you're from, I don't know, if you're from the background of AI or any background that you may have, ultimately what matters is that the applications depend on the RNG seed, and that is what we are changing. So we are basically changing the foundations layer so that everything around it benefits, okay? So certification is already deeper than a single LGI violation. We've bounded the minimum entropy from the measured LGI violation. Security against state preparation, side information is treated. Weakening certain relaxations also has been done. Memory effects have been done. What remains to make this infrastructure? Well, deployment aware certification. We are doing all these steps as we speak. Application specific thresholds and standards. Okay. End-to-end chain of trust. And this is, in fact, something which has already been done as we speak, because this slide is perhaps a month old, but I know that the group at RRI who are working on this have already done this step. Adversarial hardening beyond the optics, very, very important. And then scaling without sacrificing trust, because ultimately we would want to have a brighter source. And so, but then we can't sacrifice the trust for the brighter source. And so very live work is happening on this problem as well. So this brings us to the final layer, which is capability, okay? So when science actually survives the real world. So now, reality is route to quantum links. So what we have talked about so far is a journey where, of course, still we are talking about building a box, and it's within the lab environment, right? And then if you use it also in the bank or the defense, it is going to be in some building. But then if you talk about the links, if you talk about long distance quantum communication, then you have to go out of your comfort zone. You have to go outside, you have to face the atmosphere. While atmosphere is something we need to survive, it's a big problem for sending quantum information, okay? So this is the pivot from, theory to the messy reality that decides deployability. We have loss, we have turbulence, we have background, pointing, tracking, polarization drift, timing, synchronization, finite size statistics. So, nature does not read our project proposals. So it does exactly what it pleases. And that is, of course, all the beautiful things we write, deliverables, milestones, nothing would work if we don't put in a lot of effort to mitigate these challenges. Okay, so this is what deployability is. And so you can see this is the bench, that is what we are familiar with: benchtop experiments, protocols, different kinds of protocols, photons, rooftop. Then we go to rooftop, which is atmosphere and alignment, and then we bring in even more complexity with motion. So this brings us to something which I want to talk about for a few minutes, which is our journey in free space quantum communications through this project, which basically set all the ground-based milestones towards satellite-based quantum key distribution. Okay, and so this was India's first project in the genre of long-distance free space communications, quantum communication. So what are the achievements in this one? So of course we have achieved India's first reported end-to-end free space QKD experiment, published in an internationally peer-reviewed journal, and these rates are highly competitive, better than the previous ones. Then we went on to a first demonstration of this between buildings in our institute, where atmosphere first came in, and this was Feb 2021. This was again a first such demonstration for our country. Then in March 23, we went on to doing this with a moving platform, and I'll show you a picture of that. In fact, a video of the platform, because I think it's so nice. Everything was done within RRI workshop. They are an integral part, workshop, engineering group. They form a very important part of what we do. So the vehicle was built there. And so essentially we showed that we can actually communicate with a moving platform as well. And so this is very important because it went in straight stages, okay? So why is this important? Because you might think, not every communication happens between a stationary source and a stationary receiver. Whether it's a ship which is moving, whether it is a satellite which is moving, a drone which is moving, things move. Okay, so you have to keep pointing towards it. You have to track it and acquire data and maintain entanglement and do quantum communications. Not a straightforward task. So we did it, over several, milestones, as we call it. So linear tracking. And so, this is essentially tells you that as you move things linearly, how the correction is happening and so on, with a very nice beacon, which is centered on our detector system, which is used as the reference, right? And the receiver is moved, and how that beacon is going to essentially, change its position. And then because of our very nice feedback mechanism that we have evolved, it's going to come back. So you can see this is the central part, and this guy is now sitting here. But if we do the feedback right, it actually comes back to the center, and done this in slow motion so that the video makes sense. Otherwise, this is the general idea. And of course, at a very high precision level, this needs to be done. Then we went on to do this with a circular receiver because, as you know, satellite, in fact, has a circular arc. So am I going to be able to talk to something which is not linear? Very important. And so we managed to do that. And then, of course, we went on to do this with this platform, which was built. And so it has all the optics, optomechanics, synchronization logic that we need in order to essentially, this is our payload version 0. Okay, so everything is already there. We are doing QKD with it. And it is, a matter of miniaturizing it, making it space compatible, and then we can fly this thing. And what is very interesting and important about this is that this is actually aimed at what is called uplink based quantum key distribution, where I don't fly my source remains with me, because that is my quantum aspect. Okay, not everything in quantum technologies is quantum, so the quantum aspect is the entanglement. Okay, I retain it on ground and I send the photons up to space, to the satellite, and so this way I retain the quantum resource on ground, and that is something which has not yet been demonstrated, okay, globally. And so all the developments that we have done in this project, which ended in 2024, are milestones towards something of that nature. And so that is great because it brings in a lot of interesting possibilities of science and technology. And so we have estimated the link budget as well. Where exactly should we have these ground stations located? So we've done all the ground-based milestones. As you can see, these are the ones in green. And then we've also established, we know where to set up ground stations. Lab model is being developed, and what would remain is the qualifying model and the space model, so that we can demonstrate this, but not only demonstrate something which has been demonstrated before, but perhaps aim at demonstrating something new, which brings in more challenges and also a lot more fun, but also scientific and technology mileage, right? And so this brings us to the final part of the journey, which is the current status. Okay, National Quantum Mission is not just about links. It's not just a longer link. We are going from links to networks. Okay, and so it's not just about node A to node B to node C, which is the trusted node network. That is also happening. That is a part of our NQM journey. But we, as a our group and the consortium we are leading, we are looking at the second problem, which is about entanglement distribution-based networks, where quantum memories come in, relay repeater stations come in, entanglement swapping comes in, making it a much harder problem. But nonetheless, if this works, then we know that we have reached the next level of security, because these node-to-node ones are called trusted node networks, because you need to trust these nodes. And if we wanted to trust things in security, then there's no need for security, if you think about it. So it's good to have that as the infrastructure. And once this gets built, this can make utilization of that infrastructure going forward. And this is the, the consortium that I am leading as the PI, and Raman Research Institute is the lead institute, where we are building a multi-node quantum repeater network for entanglement distribution-based quantum communication. But as I said, NQM is not a single project journey. It is about the consortium. Every member of the consortium is equally important, because without these, we won't build this network. Okay, so we need different kinds of quantum memories. We are looking at diamond vacancy based ones, but then our colleagues, they are looking at DLCZ, somebody is looking at EIT based cold atom systems. Then we have very strong theory support, because we need to know how decoherence is going to affect us, right? We need to know what is the right repeater model to do for different platforms. So we are looking at different platforms for memories, different kinds of repeater architectures as well. And the ambitious goal is to actually have a multi-node synchronous quantum repeater network at RRI Bangalore, but then with all these memories also coming in and integrating there. Our own ones, which we are developing, our own sources, our own entanglement, but then our colleagues are also going to bring in these other kinds of memories. And so having a heterogeneous network is what we have in mind. Let's see how far it goes, because it's not, we don't have literature to refer to how to solve some of these problems, many of these problems. So we hope to create the literature as we proceed, and that is how we can actually show the success in National Quantum Mission. So what must India build next? Okay, so these are the 5 practical foundations. They have to be built together, not as decorative subcommittees. Yeah. So we need standards. So we need to certify the trust. We need test beds, because then that is where we meet the real world. We need devices, of course, which build the stack. Talent. We need to grow operators and builders. That is very crucial, right? Because without the talent, we are not going to be able to do any of this building. And then, of course, translation lab to use. So the point is not to announce foundations, it is to make them carry weight. And so, for me, capacities and capabilities are built by people. Okay, this is, of course, a snapshot of the current people in our labs. But then having said that, what is very important is that, we have students, we have engineers, we have technicians, we have theorists, experimentalists, we also have startups and institutions. So essentially, this is what I would call a national capability. And this is a little bit of a, blueprint for that. This is our own ecosystem, our own labs ecosystem. But this is what is necessary in NQM as well. The people we are, sort of training under National Quantum Mission should feel inspired to contribute back to the mission going forward. And because that is how we will be able to retain the talent that we create. So the unit of national capability is not an instrument, it is a trained human being who knows what to do when the instrument misbehaves. And so for us, behind every clean result is alignment, debugging, procurement, rejected papers, and heroic amounts of coffee. And so that is exactly how we function as a unit. Currently, we are 25 and growing. And so this is essentially what I wanted to sort of paint as a journey. So the idea being that our national quantum mission and our own mission as quantum information and computing lab have been to proceed from proof to trust to capability. And what is very heartening is that we have been able to show very good success in all these layers, not just in one or the other. And so this brings in science, engineering, technology, all under one forum. And so this is what we are building as a nation as well. And our aim is, that we build foundations so well that the future mistakes them for inevitability. And so this is what going forward will also be the mantra for our quantum journey as a nation. So with that, I think I will stop here because I have, I've kind of kept to the time and hand it back to Christine, who's currently muted. Okay, yes, now I see you.
Yeah, so thank you so much for this wonderful journey and for your enthusiasm as well. So carrying a lot of messages so that are very relevant for proving that quantum is essential for our futures as well and how we will shape this capacity as well, building a better future. Thank you so much.
Thank you. Thank you,
So
Christine.
we can start. So everyone is welcome to add your question. It might be hidden in this the Q&A different box. But then we have already a few questions for you. So we can start to read them up. So the first question from Said Adi Anjamo. So he is asking, so in the transition from quantum foundation to real world deployed, is there a framework for modeling the biological cells, so as the quantum information processing system? And we were discussing a little
We were
bit.
discussing. So I
Exactly.
think,
Perfect. I like it. Yeah.
Yeah, the person who's asked this question was probably eavesdropping on the pre-talk conversation. So, it's not as secure as we thought. And so this is a great question because, we just discussed this before the colloquium. So in fact, this is a very vibrant field right now, what is called quantum biology, where, one is trying to figure out whether, how far one can explain biological phenomena by using quantum, processes. But then having said that, this started some time ago, but only recently we have been seeing more success in people being able to map this to also experiments, which are currently happening a little bit more in the botany domain with leaves and, with things which are perhaps a little more benign than, let's say, the brain, because we don't, brain, whatever little or more we have of it, we don't want to use that as a test object immediately. But then having said that, it's a very vibrant area of research to try and model biological systems using quantum. And then on the other hand, as I was telling earlier also, to use quantum systems to understand biology better. And so photosynthesis is a prime example of something which has been much under discussion in terms of a topic like that. Also using, and that's something I didn't show because I just wanted to show a certain journey, but then, using quantum entanglement to have better imaging, for instance, which is useful going forward in imaging biological samples, perhaps helping with earlier disease detection. So these are all, ideas which are happening. So great question. I hope I answered at least a little bit of it.
And very concise and excellent response. So Alan, so we have, so your hands up, please.
Yeah.
Oh, first of all, thank you very much for this enlightening talk. I have to admit, especially after hearing your talk, I feel like photonics is going to bring us a quantum future more assuredly than other technologies in the qubit arena.
Amazing achievement that I have been able to do in this talk. So
okay,
no,
well,
but
that's
then
good.
thank you very much. That's very kind. Yeah.
I do have some like undergraduate level misunderstandings still to clear up. One of them is about QuSyn. It's intriguing that you have this startup, and I want to hear a little bit more about what what sort of product you have in mind. Is this something like a cell phone based random number generator that would be literally carried in my pocket?
Right. So that's a great question. So at the moment, of course, we are thinking of a box that you cannot carry in your pocket. So the first, I mean, QuSyn is a very new startup in some sense, and so we of course have a roadmap where we are going to take it from currently a tabletop box version, which would be this big in size, literally, because we have worked it out. So I can actually do this and show you. And so this will be used as something which will generate the random numbers, but because we have already worked out exactly how the interface will be. So you don't have to worry per se about whether it is too big or too small, because all you will do is use the random numbers directly into whatever system that you want to use it for, whether it is in
Okay.
the banking system or defense or whatever. But going forward, we are actively already researching into having a chip-based version of the same technology. But then for anything like that, I mean, what we are, of course, now particularly looking forward to is having some concerted funding, which gives us the funding for the various stages that we have in mind. So ultimately, yes, you can carry it in your pocket because it will be a chip-based version. But the first version of Q range, which will be commercial, will be a boxed version, followed
Yeah.
by the a chip. Yeah,
Okay.
that is the
Well,
trajectory.
looking forward to
And
that.
somebody saying that satellite phones don't exist no more. But then, of course, we're not talking about satellite phones. We're talking about our own pockets where you can carry a little chip which will generate randomness. And that is
Well,
what we hope to do.
it's interesting you brought up the satellite topic there because my final question is when this is really simple physics, and I'm sure I'm just overlooking uh, when you're contemplating these satellite-based experiments,
Mhm.
uh, doesn't that require extremely long coherence lengths in whatever whatever array is going to carry the information, and if and to reach those distances, it seems like you can carry no information, because you have to
That's
modulate a beam.
Yeah, so I think I agree with you that that is perhaps because I wasn't able to explain that as clearly as I would have liked to. So what we are doing is, we are in satellite-based QKD, we are not really sending the information, right? What we are doing is we are distributing the keys. So each photon, let's say one photon has a horizontal. Let's talk about polarization, which is simple to understand. So the horizontal forms the 0, then vertical is 1. Likewise, so we can sort of have some nomenclature as to what polarization state will be 0 and 1. And so what we are doing is we are sending these photons either up or down, and each photon is a key bit. So this way we are distributing the key, not the information. So once we have distributed the key, then you and I have a set of keys each, which are in real world identical because we have used, let's say, an entangled photon source, and one of the photons streams is coming to me and one of them is coming to you, and they are entangled, and so we know that we will, following certain protocols, which I'm skipping for now, we will be able to generate keys on each side, which would be identical after some classical post-processing. After that, what we will do is, I will use this set of keys to encode some information in with the key. So that is what is cryptography, right? There's nothing quantum about
Right,
this.
right,
So I
right.
want to say that, I want to go to Los Alamos. So I will then encrypt it by using zeros and ones. And so the encrypted result will look like garbage to anyone else but you, because you have the corresponding set of keys, let's say, which can be used to decrypt it. So the information sending happens through encryption and decryption, like in classical communication. It is the distribution of the keys which is made more secure using quantum. Because in classical, what happens is that you use the hardness of a mathematical problem to do the key distribution. You say that, okay, so 3 times 7 is 21. I think we all know that. But then what are the prime factors of 1, 1, 2, 3, 7, 1? That I don't think you can calculate either. And so factorization is a hard problem. Multiplication is easy, but they are, of course, the reverse of each other, but not in their hardness. So we use this to our advantage. We come up with RSA protocol, so on and so forth. So this is the standard way of doing, cryptography. But then here we have an issue that the hardness of a problem is only dependent on when something else comes along, which makes it less hard. And then a quantum computer can come along, run Shor's algorithm, and make factorization an easy problem. Then all our security collapses. That is why we need to have a paradigm change from how things are kept secure now to how we want to do it in future. And quantum key distribution is actually one of the ways of doing that, not the only way. There are algorithmic ways called post-quantum cryptography as well. But then we won't want to get into the debates on that. But it suffices to say PQC is also algorithm based. But the algorithms that are used are currently not breakable using current methods, whereas RSA has a break in quantum computers itself. But then how do you know that there won't be a break later? So the solution we always advocate is hybrid, that you have PQC enabled QKD kind of a solution. So this is a very long answer to your question, but I just thought that that's something I wasn't able to clarify in the time frame. So
Good. Well, I don't want to monopolize the Q&A, so
sure,
Christine.
yeah. Christine.
Well, thank you very much. I think the question is excellent, and it recalls as well the presentation from Professor Isara Esma, who is from South Africa, was describing last October this link as well, the longest one between South Africa and China, so through the satellite. So we remind everyone that it's also available on the Physics Matter series. So now we have, indeed, a few more questions. So for instance, so Ispa Tripathi, who is asking as well, since the quantum random number generator and the Q key, I mean, the quantum key distribution both ultimately rely on the certified quantum behavior. So how does the experimentally validate that this QRNG, so is generously producing quantum randomness and not hiding classical noise, so the noise aspect, which is important. And also you think that this QKD realistically stand today between the foundational promise and the scalable deployment. So finally, so for someone aspiring to work on this QKD, so research, so what core principle or research mindset should they hold into?
Yeah, these are all from the same person, but of course, these are three very separate questions. So I would answer the first one first, which is about, how do you distinguish between classical noise and what is truly random from underlying quantum? And that's a very, very good question. In fact, again, something I couldn't touch upon, given that there's only so much I could say in the time frame. But then if you think about it, so when I showed the results, I showed you that, for our Leggett-Garg inequality violation, the expected number was 1.32, but then the result I showed you is 1.32 plus or minus 0.03 or 0.04, because that is, the contribution from all the random error sources that exist in our experiment. And so, any experiment will have classical noise, and so that will give rise to different kinds of Poissonian errors, let's say, in different manifestations. And so we will then say that our bound is modified to 1.30 to 1.34. So anything in that range is what we are producing. But now comes the point that, the original quantum mechanical prediction was 1.5 and our modified bound is 1.32. Why is that? Because we have then also taken into account the systematic errors that are coming in from the various components that we are using, as well as any measurement based errors as well. And so we have modified the bound using quantum mechanical principles, and that is how we have a modified bound, which is always going to be lower. It can never be higher, because errors will only bring down something. And so this is how we of course know that within that error bound is what we would trust the number. So in our case the range is very small, very nice, but then it could be large as well. But then another subtle point in the LGI specific experiment for IPSA is that, in LGI, you need to do what is called non-invasive measurability. So that's something I categorically didn't talk about, because, that would have taken a few minutes to say. But suffices to say that that's one of the hardest things to do, because any measurement tends to become invasive. So we employed many interesting techniques called negative result measurement and did some clever tricks of detection as well, and were able to close this clumsiness loophole, which otherwise would give us classical noise, which can also give us very nice random numbers. And so by having a very good control on the invasiveness of our experiment in general, which is the closure of the clumsiness loophole, along with a very specific error calculation for systematic and random, we know that this is what we trust. And so based on this, what we are generating is surely coming from the underlying principles. Otherwise, easily we can mimic such bits using classical noise. And that is what is the short noise based RNGs are also available in the market, and they are using noise. right? And so this is an example. Second question, where does QKD stand between foundational promise and scalable deployment? Of course, it is much at the level of scalable deployment. Our previous speaker from South Africa must have spoken about, the link between South Africa and China, which they had achieved using satellite-based technologies. Likewise, we have, of course, had between China and Austria. So the satellite-based QKD, there have been demonstrations which of course are at a what makes a deployment is this is happening in real scale, right, like geographical scale. So naturally we are not just talking about a promise anymore. It's very difficult to call it that. Likewise, fiber QKD, we had a trusted node network again in China, which is 2,000 kilometers with nodes in between. India has also, at least according to Press Information Bureau's press release, a startup has shown 1,000-kilometer link, but there is no academic or scientific review of that. But then, we will go with this enthusiasm that startups are playing a very important role in our ecosystem as well. And then somebody aspiring to work in QKD, what core principle or research mindset should they hold on to? I don't particularly know why it should be fundamentally different from if you're working in some other sector, because your core principle or research mindset should be about always questioning what you're doing, and then trying to satisfy your colleagues with the answers, but also more so satisfying yourself. And once you know that you have satisfied all the questions that are coming to you, then whatever you are producing is worth talking about to a second person. So I don't think that principle would change just because it is QKD. So I don't think I have any QKD specific advice here, except that we have to have this understanding that there is a lot of work to do in the fundamental aspects, but then there's also very interesting work going on in the deployment sector. So QKD is a very interesting example where you can choose to work either in the foundational aspect or in deployment, depending on your interests in research, right? I hope that answers. Yeah.
A very complete answer, so thanks a lot. So indeed, so we have a bit more about also the entropy aspect. So Makaran, so Dewey, so speaking about also this quantum random number generator device, so which measures the entropy of the system, so with a fluctuation from environment, so along with some entropy fluctuation relation towards the erodicy, like the hypothesis. So something like the Slizar demon, the brothers of the Maxwell demons. So maybe can you elaborate a bit on those different demons? And can you please, maybe it's confidential also, that was
I do know Makran, as so I think maybe I can have a separate chat with him on this particular problem.
Okay.
Yeah.
Very good. Very good. So we will do this separately. So then the last question that we will have today, so from Dipanki Om, so asking that you could comment a bit further on this human capacity building at the postdoc level from this, so I guess it's the national quantum mission projects in India.
Yes, of course.
Potentially.
I'm very, I'm very glad to note that Professor Dipankar Home is with us, because he has been our theory collaborator. And as you have seen, he was there on the randomness generation paper as well. So I think, he's one of the oldest practitioners of quantum theory in India. And so it is really a blessing to have him as a collaborator. But then the human resource development and the postdoc and the national, that's a very, very good question. And I think he's coming from, having spent much more time in this ecosystem than perhaps I have, to know that this is a real problem. I mean, so we really are training manpower. We are also producing PhD students, but we sometimes some of them really have the nationalistic desire to contribute back to the ecosystem, and so they are doing that. And I'm of course particularly privileged to have many such people working with me in the lab. But then, having said that, there is of course, it is not it's apples to oranges. So, but then if you have a think about the remuneration that we are providing. So from an Indian perspective, we have a certain remuneration. But then if you see some, other currency, if you do a direct conversion, then naturally that's not a great thing to do, because our cost of living also comes in, which actually is lower than many other countries, and higher than some. So I think one thing that we have done, Professor Home, under NQM, is we have been able to because this is done in a Section 8 company mode, where we are doing this through a not-for-profit company, and it's not directly a government initiative in that sense. The government is giving money to a not-for-profit company, which in turn is disbursing the resources. So we are able to also have some special positions which can be more lucrative in terms of the remuneration, even from the even if and if that is a factor, then that is something which is being thought about. There are also some named fellowships which are happening, so that we can have at least some positions for those very deserving few who want to contribute, and also make it interesting for them from various aspects. So this is happening, but I think more will happen as we go along. Because your question is specifically about the postdoc level, so that is the answer to that. But in other levels, we are having lots of different, HRD activities through the hubs and technology groups to have a more understanding of quantum in different age groups of students, so that we really can build bottom up, even students in schools and so on. So we have initiatives where we are talking to them as well. I hope that answers. Yeah.
So maybe if so we leave him answering live. So you should be able to be unmuted. Can you speak?
Oh,
So you raise your hand, so
correct.
We can have you, please. Would you have anything to respond to the answer from Professor Sinha?
I don't know if it is an anomaly.
Yeah, I mean, he unmuted, but maybe he cannot speak. There might be potential issues with the microphone, so no problem. So I think we will just stay like that. Okay, so thank you so much for this presentation again. So the time has finished as well for this colloquium. So we are really grateful for having you with us, and then we can have possibility to see a bit more of all of that while we will be having in 1 or 2 weeks the recording available. So thank you so much for all of that.
You're most welcome, and thank you.
So
thank you very much for the opportunity.
So I think that we greatly appreciate it. And your slide, I guess, and I hope will be also available if it's possible. So we'll put it as well.
I think I just signed a form where I said that, it is okay to put it on YouTube and all that. So I think we did that before the colloquium began. So I think it's not a problem. Yeah. Thank you.
That is excellent. So thank you so much so for your participation. Very, very appreciated from everyone. So here with the audience.
Very nice audience as well. Thank you. And thank you, Alan.
Thanks a lot.
Bye-bye.
And then I will just mention the last, so the next colloquia as well that will be happening in July. So he will be, it will be live from this time Indonesia, and that will be speaking about the neutron vision, so a new windows into the enhanced oil recovery. So by Dr. Farujo Akpa, and we will be looking forward to listen to his presentation. It will be at the same time, so 10, which is in EDT, but then 4 p.m. in Europe. And we have, so now every 2 weeks, so every 2 months, the possibility to listen to new speakers, so from this Physics Matter Colloquia, and we are really happy to have possibility to also share with you, so those nice question and answer, and we'll see you next, so in July. So thank you, everyone. Bye-bye. Thanks a lot, Alan.
Bye-bye.
Bye, everyone.